So hello everyone, and thank you for being here this morning. I'm Rafael, and I'll present a study that I did with Dr. Garner that we call the effective assessment of cap beams retrofitted with externally bonded fiber reinforced polymers. First of all, I want to go over what we will discuss today, and I'll first try to justify why we're doing this in the introduction. Then I'll go over a general overview of the proposed method. Then in the next two um, sections, I'll go into details of our finite element model and the system level capacity determination. And the last two sections will be a case study that we will implement the um, proposed method. And then I'll try to draw some conclusions in the end. So, as an introduction, the average age of bridges in the United States is 42 years old. So, what that means is that most in-service bridges in the United States are being or will be experiencing some increase in loading condition due to the increase in the loading rate of the in the past decades. Because of that, a number of bridges are being deemed structurally deficient or overloaded. We have seen this situation here happening quite often, where bridges are closed for some kind of retrofit rehabilitation retrofit action. So we all know that the rehabilitation or reconstruction costs for all of the bridges there are structurally deficient or overloaded is prohibitive. And because of that, an effective analysis methodology is required in order to be able to more accurately calculate the actual capacity of these beams so we can more effectively plan our retrofit plan. Our retrofit plan, or maybe find our bridges that are more critically overloaded than the others so we can more effectively address those critical bridges, or maybe even find that our bridges with a more accurate analysis methodology, maybe they are not overloaded at all. So anyway, in this retrofit scenario, we have what we call a fiber reinforced polymers, which have gained popularity over the past decades due to their high strength, corrosion resistance, low creep, linear elastic material, and durability. And because of that, it's also gained popularity as a retrofit alternative. In this image here, I show the retrofit alternative that we will consider in this presentation, which is the externally bonded FRP retrofit, which, as the name implies, is basically bonding this FRP fabric to the outside of the existing reinforced concrete in order to increase its flexural and shear capacities. And also we have seen those same alternative approach, retrofit approach, being used for bridges as well. And here we have cap beams, which are the focus of our presentation in our study. The problem is that there is still a lack of holistic analysis too that consider the system level response, meaning the interaction between the concrete cap beam and the FRP retrofit in order to get an accurate structural capacity of these elements. Also, because we're dealing with cap beams, because of the size of those elements and how closely spaced they are normally loaded from the superstructure of the bridge, they are usually deep elements which do not follow the plane section remain plane theory, and adds into the complexity of this analysis, and then requires a different analysis method, or we should say a more comprehensive analysis method, in order to accurately account for all these interactions, in order to get us an accurate response, a reliable response of this cap beam so we can work with. So in this study, we will propose a staged analysis methodology, focused mainly into the finite element modeling approach for cap beams retrofitted with externally bonded FRP fabrics. All right, so our proposed method is comprised of 3 stages. The first 2 stages is what we call the preliminary analysis stages, and they are basically there to make sure that you even need to do a nonlinear finite element analysis of your structure, because as we all know, finite elements are both they are complex, they are time demanding, computationally demand. You don't want to do that and figure out that you could have done a simpler analysis and found that your cat being was structurally safe. So the first one is a sectional analysis, where we check our capacity and our demand. And if we find that our cat being is still not good enough, we do then a Strudentine analysis, which is the analysis type recommended by ACI and Ashto if you have a deep being element. It's more complex than a sectional analysis, but still simpler than a finite element, and you can do that to see if you have enough capacity. But if you don't, then we go into stage 3, which is where we use our finite element analysis. First, we do a finite element analysis of the cat being as it is, to check if we have a structurally safe or not element. If not, then we will need to think of some kind of retrofit alternative until we get our capacity greater than our demand. And for the sake of our presentation, this retrofit will be dealt with FRP. So this was our proposed stage analysis methodology, and now I will go into details of the finite element constitutive model, and after that the system level capacity determination. So our finite element, we did our study using the Vector2 finite element software, which is a finite element software which is dedicated exclusively to reinforced concrete. So it uses state-of-the-art modeling approaches for reinforced concrete element. It is a 2D continuum finite element model. This picture here illustrates how a model looks like in Vector2. It uses the smear rotating crack model approach and the disturbed stress field model. So the disturbed stress field model basically means that it can account for the coupled interaction of axial, flexural, and shear of the reinforced concrete. And also, it can also account for a number of second-order material behaviors that are specific for reinforced concrete that might play an important role in your system-level response. So Vector2, in Vector2 we will use a reinforced concrete, constitutive stress strain behavior that is a plastic offset based nonlinear concrete model. And for the reinforcing steel, we will consider a tripartite reinforced steel model with the compression buckling effects included as well. In the FRP modeling, to illustrate how we will include that in our model, we have here, let's say, a concrete beam wrapped by FRP fabrics, and that translates in our model into a FRP truss elements and concrete elements, where the FRP trusses spans where the FRP fabric is, and the cross-sectional of each of these truss elements is comprised of the effective width that each of these elements substitutes for the actual fabric times the thickness of this FRP fabric. Also, when we have a FRP fabric that wraps the element instead of just being glued to this face here, we will also consider the confinement effect that this wrapping causes on the concrete elements on the edges of the beam, and also the perfect bonded nodes that the wrapping provides to these fabrics. So the FRP fabrics is modeled as linear elastic. For the FRP elements that are not considered perfect bond, we will include the bond slip using those links, and for that we use the Settle and Vacuum bilinear model. So that was the specifics of the finite element. So for the system level capacity determination, we will use pushover analysis to determine the load capacity of the beam. However, we don't want to use material factors to reduce the material as reduce the material properties as the code um, indicates, because that might change the response of the finite element, because nonlinear models are highly sensitive to the material property values. For that reason, we will employ a global safety factor, this gamma g right here. So we will use a nonlinear finite element analysis with characteristic values of materials and divided by a global safety factor to get what would be a equivalent of the code design resistance of this beam. And for calculate this global safety factor, we use the estimate of the coefficient of variation method, or ECOV method, that Cervenka in his study show that yields a good result based, when you compare with more complex methods. So in this method, we need two finite element analysis, one with the characteristic material values and one with the mean values of materials. And then we use these two formulas to get the global safety factor. So now that we discuss basically this finite element constitutive model section and the system level capacity determination section were the core of the finite element proposed method of our study. And to illustrate that, we will use a cap beam case study and then a retrofit FRP study. So this cap beam is an existing cap beam. This is all the specifics of this cap beam, the loading and the reinforcing configurations. And using those two preliminary analysis stage, it was calculated to be overloaded. So we needed to do a nonlinear finite element analysis of this beam to get an accurate capacity and to get an idea of what was causing the failure of this element. This is how the same cap beam was modeled in vector 2. You can see here that we only model half of this beam due to the symmetry conditions. Those are all the specifics of the modeling of this beam. And the second order material behaviors that we consider, as I mentioned, vector 2 counts for a number of them. And these in red were the ones that were more important, let's say, for this specific beam that we are considering. Both compression softening and tension softening effects are important due to the high amounts of cracking that we were expecting for this beam due to the low amounts of reinforcing that this beam had. And also the rebar dowel action was also important to provide a little bit more shear strength to this beam due to the also small amounts of stirrups that this beam had. So the pushover analysis that we did to calculate the capacity of this beam found this stage at failure of the beam. So we can see lots of cracks, shear cracks on the cantilever, shear cracks going from the first span to the inside of the beam, and also some flexure cracks on top of the first pier right here. We can see on the bottom image that the reinforcing still has yielded with a yield strength of 40 ksi. And using the ECOV method that I mentioned before, this cap beam was found to be 22% overloaded. Therefore, we needed to perform a FRP retrofit study in order to ensure that this beam had a greater capacity than it was being demanded. So in order to do that, we needed to first develop a FRP retrofit layout that could capture what was wrong with this beam to begin with. And we did that based on the unretrofitted response of this beam. And here I'm repeating the image of the previous slide. This is the unretrofitted beam. So we could see lots of shear cracks on this span, shear cracks on this span, flexural cracks on the inner span, and considerable flexural cracks on top of the first pier. Some flexural cracks here too. So the developed FRP layout to capture and to retrofit these behaviors were this one, where the black FRP fabrics are wrapped around the element to ensure a higher shear capacity of the cantilever span and the inner spans. The blue FRP strips on the top are here to ensure a flexural capacity that we saw considerable flexural cracking. And also the green layers on the bottom are in here to ensure a flexural capacity for the inner spans as well. So these are the FRP layout that we developed. Now, on a more general approach, once we develop the layout, then we need to get the specifics of how many layers we need to ensure that this beam will have enough capacity. The way to do that is either doing preliminary hand calculations to get a sense, and then doing finite element analysis iteratively, incrementing those layers of FRP in order to get the capacity higher than the demand. In this image here, I show you the final layout that we got for this beam to ensure that this beam had enough capacity. So we see here 8 layers, 6 layers, and 3 layers. So this is how that beam was implemented with the final element. And the FRP that we used was carbon fiber. I believe this is Cicadur something. But these are the properties of this element. Modulus of elasticity, tensile strength, and thickness of the FRP fabrics that we used. As the result of the analysis, we found that the load capacity of this retrofitted element was 30% higher than the unretrofitted beam, and also the retrofitted beam had an extra capacity of 11%. And by extra capacity, I mean taking the new demand that this beam should be resisting today due to the load increase, it still has 11% capacity above that. This image here on the bottom shows the difference between the unretrofitted and the retrofitted responses for both the cantilever and the inner span of the beam. So as a conclusion, the nonlinear finite element, as I hope I showed in this presentation, was available to obtain a reliable analysis methodology. The 3-stage analysis methodology that we proposed was validated and successfully verified and calculated an accurate structural response. And also the comprehensive structural information that we got from the nonlinear analysis of this cap beam was essential for the development of an effective retrofit solution. And the general configuration of the FRP layout that I showed in this presentation, although I used it for a specific case of a cap beam, can also be applied for a general cap beam, but you will still need to figure out the specific values of how many layers of cap beam, but the general layout of the FRP can still be applied for other cap beams. And the proposed analysis and modeling methodology of the determined CFRP retrofit layout I showed increased the load capacity of the cap beam 30% based on the unretrofitted cap beam, and allowed the structure to exhibit a extra capacity of 11% to what it was supposed to resist today. So with that, I thank you very much and open up for questions.